Recording in progress.
Good evening, matinee free webinarലേക്ക് എല്ലാവർക്കും സ്വാഗതം. തിങ്കളാഴ്ച നമ്മൾ ടെക്നിക്കൽ ടോപ്പിക്കാണ് എടുക്കുന്നത്. എടുക്കുന്ന ഒരു ടെക്നോക്രാറ്റ് ആണ് എന്നുള്ളതും വളരെ പ്രത്യേകതയുണ്ട്. അതിനേക്കാളൊക്കെ ഉപരി ക്വാണ്ടം തിയറിയൊക്കെ എത്ര പോപ്പുലറായി നിൽക്കുന്ന സമയത്ത് ക്വാണ്ടം കമ്പ്യൂട്ടിംഗ് എന്ന് പറയുന്ന ഒരു വിഷയത്തെക്കുറിച്ച് തീർച്ചയായിട്ടും നമുക്ക് കേൾക്കാൻ ആഗ്രഹമുണ്ട്, അതിനെക്കുറിച്ച് അറിയാൻ ആഗ്രഹമുണ്ട്. പ്രത്യേകിച്ച് ഇപ്പോഴത്തെ ന്യൂ ജനറേഷൻ ഏറ്റവും കൂടുതൽ ശ്രദ്ധിക്കാവുന്ന ഒരു വിഷയം കൂടിയാണ്. നമ്മൾ കേട്ടിട്ടുണ്ട് കൺവെൻഷണൽ കമ്പ്യൂട്ടർ, ഡിജിറ്റൽ, അനലോഗ് കമ്പ്യൂട്ടിംഗ്, പിന്നെ പലതരത്തിലുള്ള കമ്പ്യൂട്ടിംഗ് വിഷയങ്ങളെ കുറിച്ച് കേട്ടിട്ടുണ്ട്. പക്ഷെ ക്വാണ്ടം കമ്പ്യൂട്ടിംഗ്, ഇപ്പൊ ഈ അടുത്ത കാലത്ത് ക്ലൗഡ് കമ്പ്യൂട്ടിംഗ് എന്ന് പറഞ്ഞൊരു കോൺസെപ്റ്റ് വന്നു. പക്ഷെ അതിനൊക്കെ വളരെ വ്യത്യസ്തമായി അത്രയും ഡെപ്തില് നമുക്കറിയാം. സത്യത്തില് എനർജി എന്ന് പറയുന്ന ഒരു കോൺസെപ്റ്റിൽ നിന്നുകൊണ്ട് എന്താണ് ക്വാണ്ടം കമ്പ്യൂട്ടിംഗ് എന്ന് നമ്മോട് സംസാരിക്കുന്നത് കണ്ണൻ സാറാണ്. അദ്ദേഹം വൈസ് അഡ്മിറൽ ആയിരുന്നു. പലതരത്തിലുള്ള ടെക്നോളജിക്കൽ ടോപ്പിക്കുകൾ കോർത്തിണക്കിക്കൊണ്ട് വളരെ മനോഹരമായ നല്ല ഡെപ്ത് വിത്ത് റിസർച്ച് സാറ് നമുക്ക് വേണ്ടി എല്ലാ മാസവും ഒരു പ്രോഗ്രാം ചെയ്യുന്നുണ്ട്. അപ്പം ഇന്നത്തെ ഈ പ്രോഗ്രാമിലേക്ക് നിങ്ങൾ എല്ലാവരെയും സ്വാഗതം ചെയ്യുന്നു. അതോടൊപ്പം പ്രിയപ്പെട്ട കണ്ണൻ സാറിനെ. കണ്ണൻ സാർ, യു ആർ വെൽ.
Okay. Thank you, Sabu. Thank you very much. We will start. So the topic is, what is quantum computing and where is India's vision towards achieving this? So let me give you an introduction to this. Humans have always struggled and pursued a desire to build new and modern appliances to solve mathematical functions. Over the centuries, they have been doing this, and they have been successful, sometimes with some delay, sometimes they have been quickly been able to solve the problems. And this quest took them through eras of analog computer, then digital computer, and now quantum computer is almost on the horizon. Today, digital computers are part of everybody's life, and they appear in physical form of calculator, mobile phones, laptops, etc., all achieved through semiconductor technology. For many industrial and scientific applications, conventional computers have been designed as supercomputers, specially designed as supercomputers with higher clock speed and larger memory space, because that's what makes the computer more powerful. But slowly we see a physical limitation coming in conventional digital computers. They are not able to solve complex mathematical functions. And this limitation is getting clear and visible day by day. Since 1980s, scientists have been trying to find out how does nature manage its atomic particles. How are atoms stable? Most of the atoms are very stable. How do they remain stable? How does photosynthesis takes place in plants, which helps the plants to grow? How is the light energy converted into chemical energy in photosynthesis for the plant as food? How does it happen inside the plant? How do birds navigate from one country to another country by sensing Earth's magnetic field? What is the magnetometer which they carry on their body, and how does that magnetometer which is their body work with respect to Earth's magnetic field? How are some electrical conductors, when cooled to extreme low temperatures, become superconducting materials? How do they do it? What happens in the same material, when it is cooled, it becomes superconducting? How does it happen internally? How does the atomic structure, how does atomic behavior account for this change? So they have found this very, very fascinating. And when they studied this, they found that there is a method by which we can harness this aspect of atomic behavior towards computation. And thus the family of quantum computers came hardly about 10, 12 years back. And they have started further research on that to make sure you're able to make quantum computers with different structures and different capabilities. So this is a very new field. And the takeaway for you from here is atomic behavior or subatomic behavior. Why did I say subatomic behavior? Because most of you know atoms consist of electrons and neutrons and some photons, etc. So he is looking at behavior of electrons, photons, ions, etc., and see how we can use that for computing. That is the principle in quantum computing. So let's quickly see era of analog computing. You see this picture? This is a replica of the earliest analog computer made by human being. It was used to track the position of sun and moon with respect to Earth. It was made in Greece. Its name was Antikythera mechanism. It's a Greek origin, and it was made in 100 BC. It was recovered about 100 years back from the sea. And that computer which was recovered has been kept in the museum in this island of Antikythera. And this model which was made subsequently explained how they have been able to compute the position of sun and moon. It's a set of springs and gears, etc. Mechanical computer. And analog computers, subsequently, over the centuries, we have seen many advanced versions of analog computer. They have been designed with electric motors, gears, push indicators, sine, cosine, transformers. And in the last 200 years, lots of applications of analog computer we have seen. Some have been even used for military equipment. But analog computers as a family are bulky, slow, and their accuracy is largely dependent upon how precisely you can manufacture those gears and springs and other associated mechanical items. So they had their own disadvantages. So analog computers continued till middle of 20th century. When I joined engineering, analog computers were still there, still being used, and we could wire the analog computer to solve whichever problem we wanted. But soon they got overtaken by digital computing. The era of digital computing started by middle of 20th century when the semiconductor devices were available. And the function of digital computer is like a switch, just like the switch with which you switch on the light. Either it's open or closed. When we switch on by hand, light comes or light goes off. But you can have a control for it, which can make the switch come on and come off. And they represent 0 and 1 in the binary format. This is the basic principle, basic format for digital computers. So digital computers, as I told you, they work on this logic of 0 and 1. And you have a series of hardware which are semiconductor switches or transistors, which are controlled in the hardware by some operation of the hardware. And that is normally executed through a software. So in a digital computer, you do require a software which can make the switches on and off and off and on, which will represent 1001, whatever is the one which you have to set. In a digital computer, each step of the operation corresponds to one clock pulse, one increment of the clock, which is a basic time reference. And you do the change of switches, you will get some answer, and that is stored in the memory as a result. Then the next operation starts, and it continues like that. So you require a memory which will store all this data and which will be utilized coming for the final result. So let us see the simplest computer which you have is the pocket calculator. Pocket calculators normally have 16 bits, that is 0, 1, 0, 0, 1, 0, 1, 0, like that, up to 16 numbers. And they use a clock of 1 megahertz. I'm repeating again, clock is a time reference for it to do an operation. It'll finish an operation in one clock pulse, store the data, and then it'll go to the next operation. So one step at a time, a digital computer does. Doesn't matter whether it is calculator or if it is mobile phone or laptop, whatever it is. And an interesting thing, a pocket calculator, which I said as the example, can only do addition. Even if you tell to do subtraction, it'll do only addition. How? It'll change the sign and add. That is effectively subtraction. If you want to do multiplication and division, it will shift to left, right, and then do addition. So the only thing which the pocket calculator does is addition. Just remember, rest everything is converted into addition process, and the pocket calculator does. When you enter two numbers and say multiply, the answer comes very fast. But first it converts the two numbers into 1010 format. Then it decides multiplication means it will shift right and add, and again shift right and add. All these things happen, and you will get the answer back very fast. The clock is 1 megahertz. It is 10 raised to 6 clocks in a second. So it can finish all this operation in less than a second and happen. But what happens internally is one step at a time for each clock, and only addition takes place. Now, when the speed, when the accuracy and the range of values and the complexity of the mathematics are to be enhanced, the digital computer wants more bits. 16 is not enough, give me 32. If 32 is not enough, give me 64. And it wants a clock which is faster, so that it can do the calculation very fast and give you the answer. And it also requires more memory space, because more higher the clock speed, more operations, more data to be stored in the memory, so it requires higher memory. But still it can do only one step with each clock pulse. Your takeaway is one step at a time for every clock pulse. Now, in the present day computers of desktop and laptop, you find that most of the desktop and laptops are called conventional computers now. They use semiconductor chips. And normally these clocks work around the clock of 2.5 gigahertz, that is 10 raised to 9. And supercomputers, if you are making, they go up to 3.2 gigahertz. They work very, very fast to complete the mathematical function calculation in a shorter time. Normally, they use 32 bits like your laptops, but there are machines which use 64 also. You remember all these go by steps of 2, 16, 32, 64, like that, because that is the basic scheme of the binary format. So they employ more bits. I told you the higher clock and more bits so that they can do the computation. Results are very accurate, very, very accurate, because you're doing mathematical function, you're putting the values and you're getting the answer. That is why conventional computers are deterministic. They determine the problem and get the answer accurately. This is a very important aspect of conventional computers. Their results are deterministic. Even though today conventional computers are reaching their physical limits, as I told you, they can't go higher speed. They're not able to go for more number of bits. After 64, they have to go to 128. It becomes very voluminous. The capacity is also getting limited. So research has been going on, as I told you, and studies have revealed that nature's way of algorithms, as I said earlier, photosynthesis, bird navigation, stability of atoms, they use atomic particles for controlling the computation technique. So if we use that, then we'll be able to do for larger data. But can we control a subatomic particle so accurately? Or will there be a doubt? Or will there be an uncertainty? Will it be 100% sure? Will the result be deterministic or no? These are the doubts which come in your mind. And you're right. So we need to look at these aspects. And that's how quantum mechanics has been brought into quantum computers' basic principles. So let us go and see the era of quantum computing, which is, as I told you, it's about just 10, 12 years old. Let us see that. This is C, Greek alphabet, Greek alphabet. It's normally used in quantum theory. I just want to tell you that this is a symbol. Now, as I told you, principles of quantum mechanics is used, be it electron, be it photon, be it ion, all are subatomic. That's what is used. If you're able to isolate one electron or a photon or an ion, if you're able to isolate by some method, you can control its position because it'll move. Either it'll spin this clockwise or anti-clockwise by an external magnetic field or a laser beam. If you are able to control it, then you will be able to get the results of the computing which you want to do. So net result is you get an isolated subatomic particle and control it through some magnetic field or through a laser and see what the result is. Because that is the way quantum mechanics helps you to find the solution. We'll go further and try to make it more simple. So each of these particles which you use, it forms a bit. Remember, we had 0 and 1. We used to call it bit. But in quantum computer, it's called qubit. It's another name, that's all. It's a qubit. And qubits can be 1, 0, or any combination of them. While in digital computer, it is either 1 or 0. So qubits, if you use, you get a variety of their combination, large percentage of combination. And this can be used to crunch, to handle a lot of data. That is a principle in quantum mechanics. So you use qubits for operating the computer calculation just the same way as digital computer used 0 and 1. It's an identical process, but here there is an added problem. We'll see that now. The qubits, whichever position they take, they have a probability attached to it. And this probability, which is attached to the value, which can be anything from, as all probabilities are between 0 and 1, this probability is also between 0 and 1. and therefore there is uncertainty. So quantum computing has got certain uncertainty. You're not sure. You're not sure of the solution. Please remember this. Quantum computing, you're not sure of the solution. But if you take the answer which has got the highest probability, then it is likely to be correct. So you discard all answers which are of low probability and pick up only when the highest probability. How does it do? We'll come to that. So digital computer was 0 and 1. In quantum, it can be 1 or 0, and it can be anywhere in the circle, anywhere in the circle. So that makes it able to handle a wide amount of data, but it remains uncertain. So in quantum mechanics, there are 4 laws, and I'm not going into the details, but 4 laws. Superposition, that means one qubit can have more than one possibility of states. We saw that. It can be top there or bottom here or right or left or anywhere in the circle. So that is superposition. Entanglement. 2 qubits can get entangled together and makes it very strong in correlation. This is another property in quantum mechanics. Third one, decoherence. That means qubits can clash with each other, cancel each other, decay. That can also happen. That means they will remain null and void after that. Fourth one, the environment can interfere. Suppose you are doing this quantum computing in the laboratory, and there's a magnetic field being exerted from some other instrument. Let's say there's a microwave oven there, and you're switching it on. Some magnetic effect comes, this atom will get affected, or this electron will get affected. So whenever you want to do quantum computing, that environment has to be isolated magnetically, thermally, and even vibration-wise. So you have to set up special facilities by which the quantum computing can take place in an isolated environment. Otherwise, the environment will cause some effect, and that will give you wrong answers. So look at quantum mechanics once again. You're using uncertainty, but there's a probability attached to it. You take the answer which has got the highest probability level and make sure the environment does not vitiate the answer by isolating the entire thing, putting it in a chamber which is not affected by anything which is happening outside the chamber. Now, large amount of data you can handle, as I told you, along with their probability. Now comes the interesting thing. If you are using atoms of superconducting materials, because they got advantages of superconducting materials, they take very few energy levels for transition. So if you're doing it, you have to maintain the chamber, which I told you about, at minus 273 degrees centigrade. Many of you may remember in physics, there was an absolute zero, what is called Kelvin zero. So you have to maintain the chamber at minus 273 degrees centigrade. So you require a huge refrigeration plant, a cooling plant, which will keep the chamber at the temperature so that there are no thermal effects affecting the electron, which is being controlled for the computation. Let's go forward. So what happens in quantum computing is the answer is probabilistic. In digital computer, it was deterministic. It was correct answers. But in quantum computing, the answer comes with a probability. This is correct, 80% correct. This is 5% correct, reject it. 10% correct, don't look at it, reject it. Anything which has got a high probability of occurring, then that can be a possible outcome. So quantum computers have got certain uncertainty, but they can handle a lot of data. It can be used for many applications, which I'll talk to you about, and you'll understand how this probability function is going to help. Let's go forward. So I'm going to just compare how quantum computers and this QC and how conventional computers are going to work together. So this is a very interesting diagram. Very simple, of course. Take a little time to understand it. What is in green is conventional digital computer. It can be a laptop. That's your green is your laptop. And red is the quantum computer inside the chamber, which I told you. Now, to make the quantum computer understand the question, understand the problem, a conventional computer has to output the data to quantum computer. That means it will tell, do this calculation, and this is the data, and these are the variables. The conventional computer, which is a green box, will tell the quantum computer. Quantum computer will execute that operation by controlling the isolated subatomic principle. And when it has finished the operation, the answers are measured, and that is read by the digital computer. And the one with the highest probability is taken as the most favorable outcome of the computer. This is how it works. So what do you understand? Quantum computers are an extension of your digital computer. Quantum computers not only require super-cooled chamber and so many other equipment to control electron movement, but also require a digital computer to give the data. A digital computer read the answer. So quantum computers can be seen as an extension of conventional computer. It does not have a status on its own. The quantum computer cannot do any function without a digital computer. So whenever you think you have a problem, whenever you think there's a complex situation to be analyzed and lots of data to be analyzed and crunched. Okay, let me take an example of monsoon prediction. In monsoon prediction, the monsoon occurrence depends on so many factors. Air temperature, air pressure, wind velocity, wind direction, right? Humidity, right? What is the intensity of heat which is coming in, depending on latitude. Closer to the equator, more heat. Away from the equator, less heat. So all these factors are put together. What has been the pattern in the last 15 days? What has been the variation? And then so much of data comes, you have to analyze with respect to these and then give an answer. Why do weathermen say there's a 90% possibility that you will have rain tomorrow in the afternoon? He is already saying 90% probability will have rain in the afternoon without using quantum computer. Because in conventional computer, you make a lot of simplification. You assume it will happen like this and give an answer. But the assumptions have got certain probability. That is why he says there's a good chance of rain tomorrow. When you use quantum computer for weather prediction, in association with the digital computer, you will say a little more accurately. You may be able to say 80% chance that you will have rain tomorrow. because he's able to analyze all the data in a very short period of time, which the digital computer is not able to do. So let us see how this interaction takes place. QC works along with CC, as I told you. CC will give data and algorithm to QC. QC crunches the data to give the most likely outcome. An output of QC is read by CC. This is what happens. And of course, this red square has to be inside a chamber which is super cooled. Then only it will work. So let's go further. The difference between quantum and classic computing. Classical computers, conventional computing. Power. Power means computing power, not the power which you draw from the mains. Computing power. Classic is good for day-to-day job. Whatever your laptop can do, whatever your desktop can do, it's good for the job. But quantum is good only for problems which are having lots of data and it requires complexity of a particular nature and above. Then only go to quantum. Don't unnecessarily go to quantum. To add 5 numbers, don't go to quantum. To multiply 3 numbers, don't go to quantum. You go to quantum when there are many variables, many data, and their interlinking mathematics is also depending on probability functions, etc. Then you go to quantum. Information I told you, it is like a switch on off. But a very interesting way somebody is saying, in qubits, it is not like on off, it's like a dimmer. In a dimmer, you can set the light maximum or minimum. So like that, QU bit can be minimum, maximum, anywhere it can lie between 0 and 1. Classical computers or conventional computers, error is very, very low. And it can be fixed easily if there is an error. But in quantum, you require special functions to be written, special techniques to be applied to fix any error, which can come, as I told you, errors can come from the environment, errors can come when there's a decoherence, when qubits clash and decay and collapse. So those things, you require special techniques. Then what are they good for? What is CC good for? General tasks. Quantum, where communication has to be very secure, where weather prediction has to be done, where something else has to be done, that we'll see a little later. That is where quantum computing is required, and everybody wants to go there. Conventional computers, chips, transistors are used. You're familiar with it. Quantum computers use a different type of hardware. They use quantum gates and various other connections for making sure we are able to read the movement of the isolated subatomic particles. In quantum computer, you can do all the calculations together. Many steps in one go. In conventional computer, I told you earlier, one step, one clock. In quantum computing, many steps for one clock. Quantum computers also use clock. They use about 40 gigahertz, somewhere around that area. So quantum computers can solve the problem very, very fast because they can do many calculations together, unlike conventional computers. Temperature, I already told you. Conventional works in room temperature and other requires supercooled environment. So let us see what's happening globally on quantum computing. There are 15 countries engaged in quantum research. India is one of them, recently started. But you can see in the map, whichever is colored gray, they are not working on quantum. There is Canada, USA, Netherlands, Germany, Russia, China, Korea, Japan, etc., Australia. But the leaders are China, USA, and Japan. This is a photograph of IBM's quantum computer called IBM Q. It was operationalized in 2019. This is the chamber. The circle shows the chamber. Can you see the size of the chamber? And this is the scientist standing here. How big is that computer? So quantum computers You thought of something like digital computer? Not yet. It requires a huge size mechanism. It requires super cooled, etc. The cooling is outside this, but it has to get cooled inside for all the aspects of quantum mechanics to sit inside that. I will show you the photograph inside also, but I just want to tell you the size is much, much bigger than what normally thinks of a computer. Today, everybody thinks computers, laptop and desktop, but look at this size, right? Now, this is the complex network of flexible waveguides and power connections and data connections of a quantum computer. This sits inside the drum, which I showed you. The previous slide, I showed you a huge chamber. This sits inside the chamber. And this is popularly called as the chandelier of the quantum computer. It is actually kept sealed inside the chamber, but this is a photograph of the network which is done. And the bottommost part is where the quantum computing takes place. Rest are all connections which are coming from other control devices, be it for laser or be it for magnetic field or be it for power supply, etc. So let us see what is happening. In 2011, a company called D-Wave in Canada demonstrated quantum computer and showed it to the world that quantum computers can be used. IBM released its first quantum computer in 2019. I showed you the photograph with 53 bits, with 53 qubits. And the second one has also been released by IBM with 1,000 plus qubits. 1,000 plus means the chandelier size is expected to be a little more bigger in diameter. China has established a satellite called MOSI, which uses quantum science for communication. Please pay attention to this because we are going to touch upon this topic a little later. China has got a satellite which uses quantum science in its communication network. That means it can receive a lot of data and then quickly disseminate. Most of you will know speed is the problem in satellite communication today. Satellite communication speed is a limiting factor. You can overcome that when you use quantum technique. When satellite takes a picture from space, be it a camera picture or be it an infrared signature, or it measures something else using laser, the image has to be processed and then sent to computers on the ground. And a lot of bandwidth is required for it. And this is one of the limiting factors in satellite sending data to the ground. When there is no quantum computers there, they'll be doing it at a slower speed. When they have the quantum computers, they will be able to have communication much faster and even processing the data much faster. Google has started using QC. I'm told even Apple, the latest phone, i16 or i16 Plus, has ability to exchange data with quantum computers. I have a slide on it. I'll show you. Honeywell has developed QC. So in all these operations, data size is large, complex mathematical functions, and evolving deterministic solution is time consuming. You can't wait for 10 days for a solution from the laptop or from a desktop. You don't have time. You want quick answer. Even if it is 80% correct, it's all right. Let's take it. That is the approach with quantum computing. But now they have been able to implant or embed a quantum computing process or a chip, which will be able to do the interaction with the conventional computer. I told you, you require a conventional computer to write data and read data. So they have been able to make a chip which will do this function. But the cooling plant, which is required for minus 273 degrees, will be as big as a car. So quantum computers, if you want to have, it cannot be carried by hand. It cannot be easily operated from home. It requires a very big refrigeration plant. I don't know how China has been able to achieve this in the satellite, because you require cool temperature there as well. So that needs to be further studied. How do they manage to do that? How do they overcome this problem? So Q technology or the quantum technology is advancing day by day. More companies are started using that for operations, for analyzing the data. Amazon, he wants to analyze how the customer behavior is and how products are being bought or not bought, how the market is. He wants to use computing power. He uses quantum computer. Now, can you use quantum computer without having one? We look at it as we go along. So these are the applications where quantum computers have proved themselves. First is artificial intelligence. It is being used to analyze a lot of data. Weather forecasting, I told you, is an area where you will have better weather forecasting available with quantum computing. Cyber security, I'll talk more about it later. Financial modeling, how the stock markets function, how the financial services of various banking systems can work more efficiently. Similarly for supply chain. Drug discovery, that means when you want to make a drug, let's say cancer drug, for example, and you want it of a particular strength or severity in treating the patient, depending upon patient's condition, you don't make a general purpose. Don't buy a off the shelf some drug and give to the patient. You can make a drug specialized to a particular patient. This drug is meant for patient A because his condition is like this, and he should have more of this constituent, less of this, and they should all be put together in a drug. At the same time, the chemical reaction of the compound in the drug should be completed. So to monitor all this to happen, you can use quantum computers to make sure the subatomic reactions, responses which happen within the drug manufacturer can be monitored, can be controlled by quantum computers. So this is going to be a huge step. You will be able to come out with a drug which is specific to a patient, specific to a disease, and you should be able to do it quickly through quantum computers. I told you I'll speak about cybersecurity, so let me talk a little bit about it. So quantum computers are for specialized areas like this, while conventional are for general purpose. Quantum computers can adversely affect cybersecurity, which is worrying. And I'm going to explain to you a little more. Some of the banking people here will understand it better. So let's go there. The most commonly used algorithm for cryptography in banking, in energy services, in defense services, is called RSA. It is named after 3 scientists of MIT who developed this algorithm in 1977. And since then, they have been able to get this accepted across the industries for application. Now, let us see a little bit cryptography. It is globally used by financial, energy, security services. This algorithm is based on two keys. One is a public key and one is a private key. Public key is shared by an individual when required. I have got an account. I got a public key. When I say I means I'm not as an individual. Let's say I represent an organization. There's a public key for the organization. And the private key is held with you. You also got a private key, but you don't tell anybody. You keep it with you. Now, I want to send a request to my addressee, the bank, let us say. So I want to send across to him a request, let's say, transfer so much of money from my account to so and so. I want to do this. So when I send this request to the bank, which is B sends you his public key to you. It comes back to you through the computer, his public key. When you get the public key of that organization, you send a message to the bank encrypted by B's public key. Okay, once again, A asks B for the key, B sends the key, and use the key for encrypting your message to him. Now, B decodes it using his private key, which is only with him, nobody else. And when he has decoded it, he has got the original message. A's original message has come to B, encrypted. He uses his private key and decodes it, and he gets that. This is what is being used in many of the financial services, energy services, etc. And both the keys have got long numbers, about 15, 20 digits are there. 8, 5, 6, 9, 7, 8, 4, 5, 3, 2, 4, whatever it is. Both public key and private key, both are long numbers. He multiplies them internally in his calculation, and it becomes even larger. Now, when you are given a number, a large number, and you tell what are the two factors of this, no computer can do it straight away. What are the two factors of, let us say, 21? All of us will say 3 and 7, 1 and 21. It'll give you 21. What about 97? What are the factors? 97, I don't think 97 has got any factors. May not be there. Suppose I say give the factors of 1, 3, 4, 5, 6, 7, 8, 9, 7, 8, like that, 30 digits are there. Computer is not able to find out. That is the strength of RSA. RSA has been surviving, has been having good results because conventional computers which are used by hackers are not able to get the private key and the public key separated. And therefore, they have not been able to tamper. Now, with quantum computers coming, it will factorize that multiplicand very easily. The multiplicand can be broken into private key and public key separate, and your account will be hacked. So there's a huge problem which is worrying many countries, many banking institutions, many energy service providers. How will we overcome this problem? Someone who has got a quantum computer will be able to break into our encryption easily, be it for defense services, be it for banking, be it for energy services. So there's a need for institutions to employ some other strategy of coding, which quantum computers will find it difficult. At the moment, it's not clear. So this is one of the worries of quantum computing. So let's go further. I told you some time back that how can I have a quantum computer with a refrigerant and a big chamber, etc. Don't have it. You can hire one. That is what's happening in the West now. Amazon may not have a quantum computer, He will hire it through the cloud from your home or from Amazon's office. He will send a program to the cloud. Cloud will fix up a time for him in quantum hardware. You can use the quantum computer for whatever time you ask for, and the result will come to cloud and will come back to you. Of course, you pay the money for it. Many countries have started operating quantum computers, which are located in specially isolated environment, chamber, super cooled, etc., in a building, and is accessible through a cloud for various organizations to use it. This is a trend which is happening abroad. Now, let us see what is happening in India. In India, government formalized a QC mission in April 23. They said we should be able to start, nurture it, and then scale up the technologies in quantum. What are the technologies in quantum? There are four. One, we should be able to make a quantum computing network or a quantum computer, initially with so many qubits and later with 1,000 qubits by 2032. We should be able to do secure satellite communication. We should be able to encrypt it using quantum computer. You can break it only using another quantum computer. So we should go for quantum communication. We should be able to do quantum sensing for high sensitivity magnetometers because that is required inside. I told you the electron movement or the photon movement or the ion movement is all controlled by magnetic pulses. So you require magnetometers, which we want to develop in the country. And we should have quantum materials like superconductors, which can work efficiently, though cool to minus 273 degrees, and photon detectors, etc., etc. So the government is looking at these four areas to progress research and establish Indian capability. And they've allocated 6,000 crores budget for the quantum mission for the next 8 years. That is India's. Now, what have we achieved in India? I'll just tell you. First is a communication link has been established between Sanchar Bhavan and National Informatics Center in 2023 by a quantum communication network. And today it is being used and also available for ethical hacking. If anybody can hack it, try and hack it so that we know if there is any weakness. IIT Mandi has developed photon-based qubits, and it says it can work in room temperature. Government's first QC with 25 qubits is expected to be developed by TAFR, DRDO, TCS, and is getting ready for lab trials by end of this year or early 25. Bengaluru-based startup has started building a 25 qubit QC, which he wants to do cloud services in India. I told you about cloud services in the West. So there is a startup which has said, I will make a quantum computer. I will keep it in a special place and it is accessible to whoever wants to use it through cloud network. So these are the developments which are taking place in India, very slow. It'll take some more time before we hear about. So when you read the papers, 5 months from now or 4 months from now, the first quantum computer is ready between TAFR, DRDO, and TCS. Just remember, it is 25 qubits, and they are being developed jointly by these organizations. With this, I come to the conclusions of the talk. The era of digital computers, which has lasted about 50 years, and has given us computers of different size, capability, speed, and very deterministic answers, very accurate answers for most of our computing requirement. Quantum computers, which are based on law of quantum mechanics, they can crunch a lot of data in a short period of time, much faster than conventional computers. It is getting popular. 15 countries are already engaged in research, but it has not become disruptive yet. No country has used the quantum computer as a weapon till now, but it is capable. We can use it as a weapon when you want to break the code of banking services or energy services or different services. Energy services. You know, in India, there are 4 or 5 grids. Each grid is synchronized with another based on certain protocols. Now, it is possible to make the grids go out of synchronization if somebody can hack into it. And you will have power failure in different parts of India. Worrisome. But quantum computers are capable of doing it if somebody wants to do it. It is being used as a weapon. So at the moment, it is not reached that stage, but we need to be aware of this. As I told you, the answers are probabilistic. It can be used in special types of drugs, cryptography, machine learning, weather forecasting, etc., where conventional computers cannot meet the challenge, cannot respond in the time frame which you want. As I told you, QC is a worrying thing for many services, and therefore new coding strategy has to be developed very fast. But QC requires, as I told you, isolation, cooling of facilities, etc. It is not so easily deployable like conventional computer. You require a whole lot of ancillary equipment. Ecosystem needs to be different for QC. 15 countries are already doing it. And India's mission in 2023 with public and private participation. Public is DRDO, private is Tata's and TAFR. They are hoping to come out of the first QC by end of this year or early next year. And we hope they are successful and they are able to prove with a limited number of qubits first, and they're able to march towards their next stage, which is 1,000 qubits computer by 2030. Ladies and gentlemen, with this, I come to the conclusions are over. I close my presentation. Jai Hind. Thank you.
Thank you, sir. Thank you very much. വളരെ മനോഹരമായ ഒരു സെഷൻ. എന്താണ് കമ്പ്യൂട്ടിംഗ്, അല്ലെങ്കിൽ ഏറ്റവും അഡ്വാൻസ്ഡ് കമ്പ്യൂട്ടിംഗ് എന്താണെന്നുള്ള കൃത്യമായിട്ട് സാറ് എക്സ്പ്ലെയിൻ ചെയ്തു. തീർച്ചയായിട്ടും അതിനെക്കുറിച്ചുള്ള കൂടുതൽ അറിവുകൾ നമ്മളിലേക്ക് എത്തിയെന്ന് തീർച്ചയായിട്ടും സന്തോഷിക്കാം. So I think Hariharan sir, can you start?
ഒരു പഴയ ഫിസിക്സ് സ്റ്റുഡന്റ് ആയതുകൊണ്ടായിരിക്കും ചോദിക്കുന്നത്.
ഹരിയാണോ? ഹരി.
ഓക്കെ, എന്നെയാണോ ചോദിച്ചത്?
പറഞ്ഞോളൂ.
അതെ അതെ, യെസ് സർ.
എനിവേ, I have my own doubts about this because നാളെ ബ്ലെസ്സിങ് ആയിരിക്കുമോ അല്ലെങ്കിൽ കേഴ്സ് ആയിരിക്കുമോ എന്നറിയില്ല ഈ ക്വാണ്ടം ഡെവലപ്മെന്റ് വരുന്നത്. Because he can hack into various countries, banking system, energy system. We have recently seen വെറും ഒരു പേജർ കാണിച്ച കുഴപ്പം ഇസ്രായേലാണെന്ന് ചെയ്ത് പറയുന്നു. എവിടെ നിന്ന് വരുന്നുണ്ടോ ഒരു മെസ്സേജ് കൊടുത്തപ്പോൾ ഇതുപോലെ നിങ്ങളുടെ എനർജി അത് പോവും, ബാങ്ക് സിസ്റ്റം തകർന്നു പോവും. ഇതൊക്കെ ബ്ലെസ്സിംഗ് ഡിസ്ഗൈസ് ആണോ അറിയില്ല.
People who are dealing with these services at the macro level,
ന്യൂക്ലിയർ ബാമ്പ് പോലെയാണ്
some other way.
ഹാൻഡിൽ ചെയ്യുമ്പോൾ വളരെ കെയർഫുൾ ഹാൻഡിൽ ചെയ്യില്ലെങ്കിൽ മറ്റുള്ളവർ കുഴപ്പമായി തരും. കണ്ണൻ എനിക്ക് ഡൗട്ട് ചോദിക്കാറുണ്ട്. കണ്ണൻ വാസ് ടെല്ലിംഗ് റെഫറിംഗ് ഇൻ 100 BC ആന്റി ലോക്ക് ഇത് കമ്പ്യൂട്ടർ ഉണ്ടായിരുന്നു പറയുന്നത്. ദാറ്റ് മീൻസ് ഇൻഡസ്ട്രിയൽ റവല്യൂഷന് മുമ്പേ അതൊക്കെ വന്നിരുന്നോ?
അതെ, this particular computer which was salvaged from the seabed 100 years back, and they did dating of that and found it was made in 100 BC.
നമ്മളൊക്കെ 18th century 19th century ഇൻഡസ്ട്രിയൽ റവല്യൂഷൻ വന്നത് പറയുന്നത് 100 BC
ഇൻഡസ്ട്രിയൽ റവല്യൂഷൻ വന്നത് ഞാൻ പറയുന്നില്ല. They were able to make this mechanical appliance. I've seen the photographs of in the net of the original item which has been picked up from the sea.
Thing is,
It's
as
very
early as
badly corroded.
180 BC, people could conceive and execute all these things.
They could conceive a. Now, let me say, many of you have gone abroad. You don't have to go abroad. Thiruvandaram Padmanabhaswamy temple, there is one clock
Yes, yes.
on top.
Matrimony.
Bethamani. How does it work? It has got a gear wheel with so many. When you say 12 hours are over or 60 minutes are over, the window opens through some rod and some cook sound comes. Similarly, there are so many astronomical clocks in Europe in many places, all working on gear wheels.
Yeah, no, I
And
don't dispute that. Because as early as 100 BC, ഇതൊക്കെ ഉണ്ടായിരുന്നു എന്ന് പറയുന്നത് റിവീലിംഗ് ആണെന്നാണ് ഞാൻ പറയുന്നത്.
Antikythera computer was made 100 BC. ആണ് ഡേറ്റിംഗ് നോക്കിയപ്പോൾ അവരത് കണ്ടുപിടിച്ചിരിക്കുന്ന ഇറ്റ്സ് 100 BC എന്നാണ് പറഞ്ഞത്. I have used analog computers. I have used analog computers towards final year of engineering. When digital computers are not come, they're quite okay. They're quite versatile. But digital computers are far better. Now it looks like quantum computers will be even better. But in the wrong hands, it can be a powerful weapon.
അതാണ് ബ്ലെസ്സിങ് ഇൻ ഡിസ്ഗേസ് ആണോ എന്നുള്ളതാണോ, ഡിസ്ഗേസ് ആണോ അത് കേഴ്സ് ആണോ എന്നുള്ളത് അറിയാം. Okay, thank you.
We'll come to know.
Anyway, very complicated subject.
എന്താണ്?
It's a very complicated subject. അത്ര പെട്ടെന്ന് മനസ്സിലാകത്തൊന്നുമില്ല.
No, that's why I'm keeping aside how the atom is controlled by magnetic variations and this thing. I'm not talking about that. You assume that it works.
Yes.
You require MSc physics to understand that. And you're the only one, I think, so who's MSc physics here.
കാരണം അവിടെ വേറെ ആൾക്കാരുണ്ട്, ഫിസിക്സ് പ്രൊഫസർ ഒക്കെ ഉണ്ട്.
Thanks,
sir. Thank you. Beena ma'am, can you talk?
വളരെ ഇൻട്രസ്റ്റിംഗ് ആയിട്ടുള്ള ഒരു സബ്ജക്റ്റ് ആയിരുന്നു ഇത്. ഞാൻ കരുതിയിരുന്നത് പിന്നെ ഇത് തിയറിറ്റിക്കലായിട്ട് അങ്ങനെ ഇരിക്കുന്നേ ഉള്ളൂ. ഇപ്പൊ ഒരു ഡെവലപ്മെന്റും ഉണ്ടായിട്ടില്ല, ഫിസിക്കലായിട്ടുള്ള ഒന്നും ഉണ്ടായിട്ടില്ല എന്നുള്ള ഒരു വിചാരമായിരുന്നു. പക്ഷെ ഓൾറെഡി ക്വാണ്ടം കമ്പ്യൂട്ടേഴ്സ് വർക്കിംഗ് ആയിട്ടുണ്ട് എന്ന് അറിഞ്ഞതിൽ വളരെ സന്തോഷം.
Many countries, I told you, even cloud service is available. Okay.
Okay, Roy sir.
Sorry, Roy.
The subject is very interesting, but I don't know. I hope that in 25, they found TC 1,000 to be in that. ഉണ്ടാക്കും എന്ന് പ്രതീക്ഷയിലിരിക്കുന്നു.
പ്രതീക്ഷിക്കാം നമുക്ക്.
പ്രതീക്ഷിക്കാം. ഏതായാലും ഈ കൺവെൻഷണൽ കമ്പ്യൂട്ടറും നിന്ന് ക്വാണ്ടം കമ്പ്യൂട്ടറിലേക്ക് വരുന്നതായ ആ ചേഞ്ചസും ഇതെല്ലാം ഒരു ജനറൽ ഐഡിയ കിട്ടുന്നതിന് സാറിൻ്റെ ക്ലാസ് വളരെ ഉപയോഗപ്രദമാണ്. അതുപോലെ തന്നെ സാർ പറഞ്ഞത് ഈ ക്വാണ്ടം കമ്പ്യൂട്ടർ നോട്ട് ഷ്യൂർ ഓഫ് സൊല്യൂഷൻസ് എന്ന് പറഞ്ഞ ഒരു ഭാഗമുണ്ട്. അതുപോലെ തന്നെ അൺസർട്ടനിറ്റി, പ്രോബബിലിറ്റി, റിസൾട്ട് എന്നൊക്കെ പറഞ്ഞപ്പോൾ ഇതിനെക്കുറിച്ചുള്ള ഒരു കൺക്ലൂഷൻ ആയിട്ടില്ല, ഇത് മനസ്സിലാക്കിയിട്ടുമില്ല ഇപ്പോഴത്തെ കാലഘട്ടത്തിൽ. പക്ഷേ
കറക്റ്റ് ആണ് അത്. ഇറ്റ് വിൽ ബി ഓൾവേസ് സോ because the quantum mechanics law associates probability with the type of response of the isolated subatomic particle. So I leave out the physics part of it, just a little English.
Okay.
There's always a probability to the answer. And quantum computers we should use only for those problems where you want answers, but doesn't matter it's 100% accurate or not. At least 80% accuracy, 70% accuracy is enough. And what are such
The
problems?
extension of
I
digital
told you.
computer. Listen, this is an extension of digital computer.
Without digital computer, quantum computers cannot do anything. It's only an
Okay.
extension. For problems which have got a lot of data, which digital computers cannot do, even for days or months, you give it to quantum computer.
Okay, sir.
Okay,
Yes, Apu.
Roy sir. Okay, George sir. Here. George sir undo. Gopakumar sir. Sir, ഈ അൺസർട്ടനിറ്റിയെ കുറിച്ച് പറഞ്ഞ പ്രോബബിലിറ്റി ഓഫ് അൺസർട്ടനിറ്റി ഏറ്റവും ഹയസ്റ്റ് ആയിട്ട് ക്വാണ്ടം കമ്പ്യൂട്ടറിൽ നമുക്ക് ഉപയോഗിക്കാം എന്നുള്ളതല്ലേ ഉദ്ദേശിച്ചത്? അല്ലെങ്കിൽ അൺസർട്ടനിറ്റിയെ കൂടുതൽ ക്വാണ്ടിഫൈ ചെയ്യാം എന്നുള്ള ഒരു രീതിയിലല്ലേ സാർ അത് പറഞ്ഞത്?
Uncertainty is related to probability.
Yeah.
Probability of occurrence. Anybody else?
ഗോമർ സാർ ഉണ്ടോ? ജോർജ് സാർ അറിയില്ല.
I know the topic is a little heavy in engineering. So I can see Gopakumar there.
Gopakumar is
Are
an
there any
ISR.
engineers?
He's an also engineer. He is from ISRO and George sir from Navy.
പറഞ്ഞോളൂ. ആരാത്?
Topic is very heavy. Okay. Okay, sir. Thank you. ഇല്ല സാർ അവര് ഓപ്പൺ ആക്കിയിട്ടില്ല.
അപ്പൊ ഞാൻ പോട്ടെ, ലീവ് ചെയ്തട്ടെ.
Sure, sir. Sure, sir. Thank you, sir. Thank you very much.
Thank you.
We are waiting
Bye,
for
Hari.
next.
Thank you.
Yeah, bye. See you.